you're not alone in doing the search. So in the earlier examples, okay, just a minute, this message is being recorded. Okay, got it. So in our earlier examples, earlier search problems like a 15 puzzle or n queens, your algorithm or the AI agent, the computer was the only one involved. So the computer was exploring the search space, making decisions in order to find a path from a start state to a goal state. And that's it. Now we are going to talk about problems where there will be not only the computer in the picture, but also some other agent. And that agent is going to be an adversary. Adversary meaning that it's going to be against the computer. So if you have given some tasks to the computer of achieving finding a path from a start state to a goal state, due to the presence of another agent, an adversary agent, that adversary agent will always try to make the computer or the AI agent not achieve its goal, right? So it's adversary, it's against the AI agent. That makes sense. So you have given a task to the computer. Your computer would like to achieve that task, but it's not alone. Whenever it takes an action, whenever the computer program makes an action to change its state, there is another agent, maybe one or more, there may be one or more other agents together who would like to ensure that the computer is not successful in achieving its goal. So it's adversary. It's so that the agent is now has to now fight against other agents. Right, so that's the setting. So in such a setting where your agent is not alone, you want to achieve a goal in the presence of adversaries is the scenario. So how do we achieve algorithmically our goals? So that's the discussion today. So a typical such scenario where such an adversary comes in the picture are games. For example, two-player games. So your computer could be one of the player, and the opponent will be another agent, right? So I assume that you have your computer playing a game of chess, and the goal that you would like your AI agent to achieve is to select a sequence of moves in the game of chess such that you defeat your opponent, right? The new thing is now it's not just a search problem like we had discussed earlier. Because you have a presence of an opponent who is also going to make moves alternatively, right? So your AI agent, your computer in the game of chess, let's say, if you have an AI agent automated chess player who is making a move, then alternatively there will be an opponent which could be a human being, could be another computer, could be maybe the world chess champion, whatever. There is an adversary who is going to play against your AI agent. And that's an adversarial agent because the purpose of that other agent who is playing against your program is to defeat you. Right? That's the purpose. So in such a scenario, how would you like to come up with a winning strategy? How is your AI program going to come up with a strategy of playing a game, let's say chess, so that no matter how your opponent plays, no matter how good is your opponent, there is a chance that your AI program is going to win the game against your opponent. So what are the algorithms by which we can come up with a winning strategy is the subject of discussion today. All right, so let's get back to some motivation. Why are we interested in such adversarial search problems? Number one, because playing games automatically comes or falls into this realm of adversarial search. For example, like bridge, it's a multiplayer game. Chess, it's a two-player game. Backgammon, etc. So games where you have more than one agent involved, more than one player involved, falls into the realm or category of adversarial searching. Now, why is game playing important? Game playing has been important for so games have been an important intellectual exercise for human beings, an interest for human beings, way long back in the past. For example, chess has been there and has occupied human minds for more than 1,400 years. Games like backgammon are also very old. So they have occupied human mind, number one. People find interest in playing games. Not only that, it is intellectually stimulating, and we sometimes or very often judge intellectual capability or intellectual proneness of a human being by how well that human plays a certain game like chess. So if you have a friend who's playing chess and he's winning chess games very often, a chess champion, let's say, you would give a tag that, well, that guy is very intelligent. He plays chess very well. So for same reasons, because intelligence is associated with game playing, it has found interest in the AI community. So AI researchers wanted to see, can we build computer programs which are intelligent and as intelligent that it can defeat human beings, or can it at least give good competition to human adversaries? So that's the motivation why we would like to see game playing in today's discussion. So it's a good reasoning problem. It's formal and non-trivial. Games are actually non-trivial. Like chess, you need a lot of expertise to play good chess. Direct comparison with humans and other computer programs is easy. You can compare like how good is your program against your fellow mates program if you play against each other. Right. So with this motivation, we would also like to know for today's discussion, or in the context of our course, what kind of games are we interested in? So for our discussion in the course, we will be talking about particularly two-player games like chess. Right. So one of the player will be your computer, your AI program, and the other adversary, the other player will be the adversary who is going to play against your program. And that adversary could be another program, another AI agent, or could be a human being. The second characteristic of the games that we are going to consider is that the games will consist of sequence of moves. Right? So your game should be a game which has this concept of sequence of moves. There must be some rules which specify which moves are valid and which are invalid moves. Like just compare it with the game of chess. The game chess consists of moves made by the player in an alternate fashion. And when you make moves, you follow certain rules. Not all moves are valid. Rules also specify some measure of award or reward given to each of the player. So there is a notion of reward associated with each move that a player makes. Right, and your objective, there will be an objective, of course, in the game. Like in the game of chess, your objective is to have your opponent defeated by putting the game state in such your goal will be to take the game to such a state in which the opponent has no chance of winning but to sacrifice its king. So that's the objective, and in the program, this objective is captured by means of a utility function which you want to maximize. So your AI agent, if it is playing a game of chess, it would like to maximize a utility function. The utility function is a function on the state of the game. A state of the game in the example of chess will be a board configuration, and each board configuration will be associated with certain cost, and that cost will give you a measure of how well are you positioned in the current ongoing game. Right, so we'll see more details about it. Right, so a quick recap: we will see at two-player games. We are going to look at two-player games games will be consisting of moves. Moves will be restricted by rules, and we have an objective function that the AI agent would like to maximize when it's playing the game. Right. So let's try to compare how game playing or adversarial search compares with the search problems that we have already seen. The major difference comes in point number 1, where you have an unpredictable opponent, which we did not have in a search problem. So you specify a move and you have no idea of how your opponent is going to take its move. And that's where the unpredictability comes. And due to this unpredictability, you don't have a knowledge, a deterministic knowledge of in which state the game will be after you have made a move. Right? Because the final state of the game after a couple of moves will not only depend on your move, your AI agent's move, but it will also depend on the adversary's move. Right? So this unpredictability is the major difference that we want to tackle in adversarial search algorithms when compared to our previous search algorithms, where there was no presence of such adversaries. The second difference is the time factor. The time factor means that the games, even the simplest games like tic-tac-toe, the crosses and knots game that all of us have played, they have quite a large search space. So tic-tac-toe search space is not so large, but if you consider the game of chess, the search space is huge. It's order of 10 to the power 40. So in such a large state space, there is no hope of finding an optimal winning strategy. So you cannot find a deterministic a winning strategy, a path from the start state to a goal state, if by exploring such a large state space by any of the search algorithms that we have seen earlier. So that means that because we don't have a hope of doing an exhaustive state space exploration and come up with an optimal strategy of winning, we have to come up with algorithms which look at a part of the state space, maybe some of the moves, maybe 5 moves ahead, and a few possibilities that the adversary could make up to, let's say, 5 levels, and based on that it should decide what is the best move that the agent can take based on this limited view of the state space into the picture. So these are the two challenges in addition. Number 1, unpredictable opponent. Number 2, huge spaces and limited time, and therefore you would like to come up with kind of an approximate move which is best in the sense good enough. Good enough is a good word. Okay, so this is an algorithm that an algorithmic representation of how your 2-player game proceeds. So the first box, the rectangular box, depicts the move by your opponent. Due to the move by your opponent, a new state is generated. Now that new state could be such a state which is a game over state, like a checkmate. Your opponent has put you in a checkmate. If the game is over, then you terminate. If the game is not over, you still have, if the game can continue, then the AI agent should generate the successors. From the current state, what all next moves can be applied, and due to the application of those next actions, what are the new successor states in the example of chess? What are the new board configurations that could be generated? So for each of the successors, you then evaluate by means of some measure these successors, like how good are the successors. So if you have, let's say, 1,000 successors from a given current state of the game, you would like to evaluate those 1,000 successors to come up with that successor which is the most likely to take you to the winning checkmate position, right? So you would like to have a measure of a utility function that gives you a measure of how good is a successor. But once you have such a function, you would like to choose a successor which is most highest valued, and you would like to make a move that takes you to that most valued successor as the next state of the game. Once you do that, the opponent comes into the picture, and if the opponent has no move and you meaning the AI agent has come to a game over state, then you terminate. Otherwise, the same loop proceeds. So the opponent takes a move, a new state is generated, and so on. So this loop continues until the game is over. Right? Makes sense? Two-player game.
Sir, high value successor means in terms of winning the game, basically.
In terms of winning the game, right?
In terms of winning the game, basically, how close the agent is to win the game.
Yeah, so here the closeness, so it gives a measure of if you go to that state, then what is the likelihood that you will lead to winning state. Yes. Yeah, so you can say if you are very close to winning from that state, then it has a very high value, right? Right, so we are going to discuss today how such two-player games could be formulated as an adversarial search problem. So in our adversarial search problem setting, these are the components that we have. Number one, it has states like we had earlier. Right, in the chess game or any board game, you have a board configuration as a state. You also know about initial state. You know about successor function, which returns from a current state. If a certain move is taken, then what is the next state? And there is additionally there is a test of terminal. There is a function called terminal test function, which determines when the game is over. So it takes a state and it outputs a yes if the game has terminated, or no otherwise. And this is the new thing that we see for the first time in adversarial search algorithm, which is the last point, a utility function. A utility function takes a state of the game and it outputs a value, and that value is the evaluation of that state. Like in the last slide that we were discussing, it's going to give a measure of how good is that state for the AI agent. So it gives a numeric value in terminal states. Particularly now there is a slight distinction. So here, when we are talking about the algorithms now onwards, utility function is going to be applicable to only the states which are the terminal states when the game is over, a state where the game is over, not to other states where the game is continuing. Right? So utility function doesn't give you a value to every state in the search space of the game. It gives a value to those states which are the terminal states. So those states which passes the terminal test function. Oops, just a minute. Yeah, so those states which pass the terminal test function, meaning the states where the game is over, for those states you can apply the utility function and get a value. Right. Yeah. So the value in our discussion will be either +1, which would mean that the AI agent has won the game if it is ending in that particular state. The utility function for a terminal state could be -1, which means that the AI agent has lost the game if the terminal state has -1 value, and 0 if the AI agent has made a draw with the opponent. So these are the three values that the utility function can give you. And the reason why we assume only these three values is because I forgot to mention earlier that we are only focusing on zero-sum games. Zero-sum games are those kind of games where one of the opponents is going to definitely win and the other is going to lose, or there could be a draw. It's never a win-win situation. It will never be the case that both the opponent and the agent has won simultaneously. There's no win-win. If one has to win, the other has to lose. That's what zero-sum game means. Yeah, the total sum should be 0. If AI agent wins +1, then that automatically implies that the opponent has a utility function of -1, and that the sum becomes 0. If it is a draw, then both the AI agent and the opponent has a utility function value of that state to be 0, so the sum is 0. All right, so these are the 5 components that will be given to us when we are doing adversarial search with an algorithm. So let's go ahead and let's try to understand what is a game tree. Right, so this is a partial view of a game tree in the case of a tic-tac-toe game. All of you, I'm sure, have played this tic-tac-toe game. It's crosses and noughts. You put in this 9-cell matrix or grid, and you win if whichever that player wins, which gets 3 consecutive crosses or 3 consecutive noughts in a diagonal or in a row or a column. Right. So our the exercise that we are going to do now is we will try to map the 5 components that we have seen in the previous slide into the picture. So the initial state is this empty board configuration shown as the root of the tree. So empty board configuration is when the game starts. Now there is some terminology. Look at the left-hand side column shown with max x and min 0. The meaning of a max node is that the AI agent is going to make a move in a max node. So those nodes which are those nodes which are in the max layer in this picture are the nodes where the turn of the player is the AI agent. The AI agent has the turn to play, right? And alternatively, those layers where the title is min, that is the state where the opponent is going to take a move. Makes sense? So initially, because it is max, root is tagged max, and root is playing with a cross, we say max cross. So initial state is assumed to be a state where your AI agent is going to make the move. This is just an assumption. In a game, maybe the opponent can also make the first move, but this tree is assuming that your AI agent is starting the game with the first move, and therefore the first state, initial state, is tagged with a max, is tagged as a max node. Makes sense? So once the AI agent makes a move, it can make a move with 9 possibilities. Each of the 9 possibilities is shown in the game tree in level 1, right? Depending on where the cross has been put by the AI agent. True. So far so good. So up to this layer, everything is very similar to our previous search algorithm discussions. Now is the difference. Now is in layer 1. The turn is not the AI agent's turn, but it is the opponent's turn. The opponent who is playing with a knot, and that opponent now has 8 options to put its knot. Right? If the AI agent has taken a cross in the left, put the cross in the leftmost upper top corner, then for that particular choice made by the AI agent, the opponent, which is shown by min, has 8 possible places to put the knot. Right? So altogether, in layer 2, there will be 9 into 8 nodes. Why 9 into 8 nodes? So there are 9 nodes in layer 1, and for each of the 9 nodes, there are 8 possible next states, depending on where the knot is put. So 9 into 8 nodes will be the possible outcomes of the game after two moves, one move by the AI agent, the max player, and the other move by the opponent, which is the min player. Right? Is the discussion making sense so far?
Yes, sir.
All right. Okay. Right. So this just continue this way. So once max and min has played their move, the game will be in one of the 9 into 8 states. From each of those 9 into 8 states, a move will be now made by max player, and there are 7 choices with the max to put the cross. So in layer 3, which is the max layer, because max takes the turn, it has, so the layer 3 will be having 9 into 8 into 7 such nodes in the game tree. And this way, that search tree is built until you reach the leaf nodes in the tree. Leaf nodes in the tree are those states where the game is complete. Yeah, you have anybody asking something?
Yes, so like for every turn that is made, there has to be like a search operation to see which board configuration it is in, and then proceed the tree from there.
For every move that is made by a player, there has to be a search. Can you say your question? Repeat your
Search
question.
operation, like for every move that is there the need to, like, we have to do that, like to have a search operation and check the which state the board is in right now, and then the next move proceeds from there. The tree proceeds from there after that.
All right. So Bitan, we have not started discussing the solution yet. So we are not discussing yet how do we come up with a winning strategy for an AI agent. We are just discussing that the game consists of these many states which you can draw as a game tree.
Oh, okay.
Yeah, so I'm just trying to give you a view of the game search space in the form of a game tree. Right. The next question will be, given this game tree, how do we come up with a winning strategy for the AI agents? That's the next question. So at that point, we will see how to do search and where to do search, etc.
Okay, sir.
All right. So this is the search space. So the levels have alternation of max and min players. So max player is the AI agent, min player is the opponent, and the terminal states, the leaf nodes of the game tree, are the states of the game where the game has terminated. So in the tic-tac-toe example, you can see that the leaf nodes are those nodes where the game is over, like the leftmost leaf. If you see, the game is over because the opponent has won by putting 3 knots together. And that's why the utility function value associated to that state is -1, given -1 since opponent is winning. The utility function for the second leaf node from the left is 0 because it's a draw. No player has won. And the third state from the left, the utility function value is +1 because there's a diagonal of crosses. That means the AI agent has won. So and so on. So every terminal state is associated with a utility function, -1, 0, or +1, depending on which of the two agent has won. Right. So a question to you, just for all of you to just do a warm up. The question is, what will be the number of nodes in the leaf level, or how many leaf nodes will be there in the game tree of a tic-tac-toe?
Sir, for each level, it decreased by 1. Like for first level, it is we can arrange it like
9 positions.
9.
Yeah. In second, it's not 9 square, but it's 9 into 8.
9 into 8. Like
Right.
9 into 8 means it's 9 factorial. Like for like for first level 9, then 8.
Right, right.
Multiply again 7. Is decrease up to 1, like it is 9.
Correct. 9 factorial. That's the answer, right? So you have 9 factorial leaves in the game tree. Right answer. Okay, that's good. Just one thing that we would like to understand is what is so special about the name max and min? Why are we giving the name, the AI agent or the computer, the name of max, and why is the opponent given a name of min? There is a reason, and the reason is that the purpose of the AI agent is going to be maximizing the utility function, or the purpose of the AI agent will be to take the game to a state where the utility function is maximum, right? So why maximum? Because you see, we are assigning +1 to a state which is a winning state for a computer. So a computer will try to have a strategy of playing such that it maximizes the utility function of the terminal state, and that's why the name max is associated to the AI agent. Whereas the adversary, which is your opponent, would always try to minimize the utility function of the terminal state. So this is where the conflict comes. You are playing in terms, and the purpose of the AI agent is maximizing the utility function. Take the game to a board position where the utility value is +1. Whereas your opponent is just trying to do the opposite. It's trying to take the game to a -1 state. So this is where the conflict is lying, and this is where your algorithm has to therefore defeat your opponent. It has to come up with a strategy which says that no matter what move your opponent does, of which you have no control, your strategy, the agent strategy, is always going to try taking the game towards a high utility terminal state. Right. So here the winning strategy, try to understand here that the winning strategy of the AI agent is not going to be a path, right? Like our previous search algorithms, the solution has been a path which is a sequence of actions which takes you from the initial state to a goal state. Here, for adversarial search problems, the solution is going to be in the form of a tree. The reason being that, so you start the game in a root initial state. The AI agent, let's say, has a strategy of making a move. Let's say it puts action A first as its move number 1. Once the AI agent has taken the action, the opponent, what the opponent is going to do, the AI agent has no control on. So if there are, let's say, 10 possible outcomes that the opponent is going to can possibly make, your winning strategy has to provide you an action for each of the possible 10 moves that your opponent has taken, right? So let me just try to use the board to discuss the winning strategy a little. Can you see the board, by the way? See, is it visible?
Yes, sir. Yes, sir. It is visible.
Okay. So your game starts with an initial state. This is where your AI agent, the max agent, is making a move. It has made so as part of the winning strategy, let's say the strategy is for the max agent is apply an action A1 and go apply an action A1 and go to a state which is this new state. Now this is where your min comes into the picture, and min has 10 possible outcomes, 10 possible actions that it can take. It can take B1 and B2, and so on, and let's say some n number of actions, finitely many. Now you have no control on what min is doing. So the solution, so I'm trying to draw a winning strategy as a tree. The winning strategy for the game, for the AI agent is start playing an action A1. Now, depending on whatever move min has taken, your strategy must have a reply for every possible outcome made by min. So your strategy will be, if min has played B1, then max plays a move, which is, let's say, C1. If min has played B2, then max makes a move C2, and so on. Again, min, again, min, again, max. Right? So your AI agent must have a solution, which is this tree. This tree is a solution because your AI algorithm can refer to this tree to determine how to play the game. So it will start the game by making a move A1. Now, depending on what min has played, the game of the state of the game will be in one of the n positions. Depending on which position the game has gone to, you are ready with your next move. Your strategy, you have a strategy ready. Like if B2 was the move, then AI agent will refer to this tree and it will say, oh, B2 is the move. So my next move is C2. I will take this winning move. My strategy takes C2 as an action and go to this move state. Now the min takes one of the moves out of the n, and depending on which state it has taken, you are ready with the next D1 action in this layer, right? So your solution is not just a path, like in the n queens problem. Put a chess, put a queen in position ij, then put a queen in position I prime, j prime, and so on. No, here the solution is a tree, which is a contingency plan. It's like it's not only a path, it's a tree, because it has to take into consideration all possible moves at each point the min comes into the picture and how to react to each such possibility. Right? All right, so I think good discussion on game tree. Now let us come to some terminology. I think we have discussed these. We can jump to the algorithm right away. Maybe a quick discussion. So we are referring to a move by so there is we are talking about a move by up player as a ply. So a move which is made by one of the players, maybe the agent or the opponent, we refer to it as a ply, and two plies make a move. So that's a move is not just one player's move, it's a consecutive play by two players. That is what makes a move in the discussion. Okay, we have referred what is a utility function. Backed up value, just hold on for a moment. It will be clear with an example. What is a minimax procedure? I think it will be better if we proceed to this figure and understand this algorithm, which is called the minimax algorithm. And this is an algorithm which is going to give us this winning strategy for a given game. Okay, the figure is a little hazy, but I think we can read it. Maybe if I can make it small. Okay, let us try to understand the minimax algorithm. The minimax algorithm assigns a minimax value to each node of the game tree. Okay, so this is an example in slide 10. If you see in slide 10, this is an example of a game tree, a very small game tree with just one move, that is two plies. one ply by max followed by a ply by min. Let me just clarify the meaning of the picture. So the triangle, the nodes which are marked with a triangle are max nodes, meaning those nodes at max nodes, the AI agent is going to make a play. It's going to select a move. Whereas the nodes which are represented by inverted triangles in this figure layer number 1, those nodes are where your opponent or the min player is going to take a move. Make sense? The meaning? Yeah, up triangles.
Yes, sir. Yes, sir. Yes, sir. So up triangle means max, and downwards means it's min.
Right. Perfect. So the edges in the tree represent what actions have been applied in the game. And in this example, we are assuming that there are 3 options for both the max and the min player at each point, at each state. Right. So in starting from the root, the max can apply one of the 3 actions, which is A1, A2, A3. And depending on that, the next state is determined, which is a min node. And the min node again has 3 options. So if the max node has selected A2, then the game tree is in state 2, and min node can take A21, A22, or A23, one of the 3 actions as a reply. And as a result, you end up in the max node again, which is the layer 2 or the leaf nodes here. But this is, we consider a very small two ply one move game for understanding the minimax. So this small game tree is enough to understand the algorithm. Once we understand it, you can apply it to larger games. So I have a larger game in the next slides where we will apply the minimax algorithm once we have understood it, just to verify. All right. So the values, each node is associated with a minimax value. Okay, and the purpose of the algorithm minimax is to calculate the minimax value of each node. Now the question is, how do you calculate this minimax values? Okay, if the node is a leaf node, then the minimax value of that leaf node is just the utility function of that node. Right? No, recall that we said earlier that every terminal state has a utility function value. Every terminal state, meaning every leaf node of the game tree, has a utility function, and that will be given to us as part of the problem specification. Utility function is given. So you have the values of 3, 12, 18 up to 2 given for each node of each of the leaf nodes of the given game tree. Okay.
So value, basically the function assign the value only for leaf node, not for
right.
The predecessor nodes. Like
utility function. Utility function is defined only for leaf nodes, not for internal
nodes.
Right.
Okay.
Utility function is given to you, and you can just look up the utility function, and minimax value of a leaf node is equal to the utility function of that node. Okay. So what is now remaining is how to calculate the minimax value of the remaining 4 nodes, the root node and the level 1 nodes. Right. To understand that, we will first understand what is the meaning of a minimax value of a node. So consider the leftmost node of layer 1, which is the lower triangle, the inverted triangle node, min node, the leftmost one in the picture, which has a value of 3 associated with it. So how do we get the value of 3 here? So the value 3 here means the following. It means that what is the optimal, what is the minimum utility function of that state, given that both the players play optimally from that point onwards. Okay, let me try to clarify. So in the min node, leftmost min node, you have three possible choices. Your opponent has three possible choices of playing the game: A11, A12, A13. If it chooses A11, then the utility of the state that it goes to is 3. Similarly, if it chooses A12 and A13, the utility of the game, or the utility of the resulting state becomes 12 and 8 respectively. Now, out of these 3 moves, because the goal of the min player, the goal of your opponent will be always to minimize the utility function value. In order for the opponent to win, the strategy that the min player would like to choose at this point, at this state, is A11 and not the other two actions, A12 and A13 respectively. Right? You see the point why, right? So min player, the goal of the min player is to minimize the utility function, because if it is able to minimize it, the chances of the min players winning increases. And the goal of the max player is to always take the game to a state where the utility function is maximum. Now, with keeping that in mind, if the opponent is in leftmost node of layer 1, it has 3 choices, and the opponent sees. So the algorithm, rather the opponent knows what is the utility function value for each of the terminal states due to the result of A11, A12, and A13 respectively, right? Because it's given as part of the problem specification, which is 3, 12, and 8 respectively. Now, out of that, because the state, the leftmost state is having the smallest utility function 3, the strategy for the opponent will be to apply A11 at that point, because that's the minimum. That's the minimum.
Sure. So first, initially, if max, let's say, take the step A1, and after that, the in turn of minimum, like opponent, the opponent decide to take A11 because
because that's the best it can do.
That's
the best. Absolutely. Yeah, that's the idea. If the max player has taken A1, the best move that the opponent can take is to apply A11, because that is the move which is going to lead to the state which is having the minimum utility value 3 in this example.
Okay, right? If AI agent take the move A1, then the opponent will take
A11
because
right.
He trying to minimize the
utility.
AI agent.
Yeah,
like,
that's exactly the case. Yeah, so that's why you put 3 as the minimax value of the min node there. So this value tells that what is the best that the opponent can do. What is the smallest utility function that the opponent could lead to from that point onward? In this example, it is 3. Best, right? So opponents best means opponent
Sir, you are not audible.
Hello?
Yes, sir. Now you are
Now
audible.
it's audible. Okay. So I was saying that move to the middle node. The idea is all the same. If the game proceeds to the node, which is the middle node of layer one, that's a min node. And because it's a min node, you would like to put a value 2, because that is the best value that the opponent can take, can achieve from that node onwards. If the opponent is playing optimally. If the opponent is playing optimally, then it can, the best it can achieve is value 2. Right? Similarly, 2 is the minimax value for the last node in layer 1. Now come to the root node. Root node is the max node, and the goal of the max node is to maximize the utility function. Now that you know the value 322 of layer 1, right? The AI agent knows that if it takes A1, then the best that the opponent can.
Sir, again, you are not audible.
I don't know why is it getting switched off. Am I audible? Oh, there is a battery issue. Just a minute, I have to change battery. Hold on.
Okay, sir.
Am I audible now? Hello?
Yes, sir.
Yes, sir, you are.
Okay, I got a new battery. Right. So, so similarly, for each min node in this tree, you look at its successors and you see their utility for function values, and you choose that value which is the minimum out of that, and that value tells that if the game is in that particular min node, then the best the opponent, the min player, can take the game to is to a state which has a utility of 2. Right. So once you have calculated 3, 2, 2, you can come to the calculation of the minimax value of the root. Here, your objective, the AI agent's objective, is to maximize the utility function of the utility function. So the AI agent sees that it has 3 alternatives to play: A1, A2, A3. If it plays A1, then the opponent min player has a the opponent min can possibly take the game to a state with which is 3, right? If it is playing optimally. Similarly, if the max player selects A2 and A3 respectively, the opponent can drive the game to a utility terminal state which has a utility of 2 and 2 respectively. So with this knowledge, the strategy that the max player should have in the root is to select A1, and the value of the minimax value of the root will be the maximum of the minimax value of the children's. You see why maximum, right? So it has 3 choices. If it chooses A2, then it the min player can drive the game to a 2 utility terminal state. Similarly for A3, but if the max chooses A1, then if the minima from that min player from that point onwards play optimally, then the max player gets 3 utility function state. So that's better for max. Its objective being to maximize the utility function of the terminal state.
Okay, so the reason is basically 3 is greater than like other. For if the AI agent take the step A2 and A3, then the opponent will take will choose the step is 2 and again 2. So
Right.
3 is greater than 2. So for this reason,
Right. That's the point. So therefore, the winning strategy, now that you have calculated the minimax values, you get the winning strategy, which is the AI agent will select A1 as at the level 1, and then whatever min does, the value of the game will be definitely more than 3. So the value minimax 3 for the root tells you the minimum utility function that you meaning the AI agent is guaranteed, no matter how your opponent plays. Now, this is an important point. No matter how your opponent plays, you are guaranteed to have a minimum utility of 3, if not more. Right? Because your opponent can play suboptimally also. So like if the AI agent takes action A1 and your opponent is not an experienced player, it takes a bad move and selects A12. Right? As a result, what happens? The utility of the game is 12, and that's even better for the max player. The AI agent will be more than happy because 12 is much larger than 3. Similarly, if it selects A13, the game terminates in 8, which is more than 3. Right? The point here is that the minimax value of the root 3 tells that the game when it terminates is going to have a utility which is at least 3, and it will be exactly equal to 3 if your opponent plays optimally from that point onwards. All right, makes sense?
yes, sir.
Okay, so another point to observe here is that this winning strategy it may not be an optimal strategy. An optimal strategy meaning a strategy which optimizes the utility function, may not be the optimal strategy. So in this example, which state would be the best state that for the AI agent to terminate the game? Out of the 9 terminal states in this slide, which node will be the best node for the AI agent to achieve?
Sir, which picture, like?
Oh, this picture, this old picture, small
Yes.
tree.
Okay, then it is obviously 3.
No. So no, not actually. So my question is that, so you see the 9 states in the terminal, right? Each of them has a utility function,
Yes.
which tells you the value of that state when it terminates in that state.
Okay.
Now the goal of the max player, the AI function, is to maximize the utility function. So my question is, which state will be the best state for the AI agent to terminate out of the 9 states in the leaf level?
It is 14.
14, right?
Yes,
14.
It is 14, right? Because if the game ends in 14, then that is the best that the agent can do, maximum.
Yes.
And it's going to be worse if the game terminates in A221 and A33, the nodes which has a value of 2. If the game terminates there, it will be the worst for the agent, but the best for the opponent. True?
Yes.
Right. So now that's the best utility function that one can achieve in this game, in this simple one move game. However, the optimal strategy that we have just come up with is never going to give you a utility function value of 14. You see why? Because what is your winning strategy? Your winning strategy is take A1. And once you take A1, no matter how bad your opponent plays, the best you can achieve is value 12, which is suboptimal.
Yes.
Right? So this shows that the algorithm that we just has, the minimax algorithm for coming up with a minimax, for coming up with a winning strategy that we have just come across, is not going to give you the optimal strategy. However, it gives you a lower bound on the utility function, in the sense that it tells you what is the minimum utility function that is guaranteed to be obtained if you play according to the strategy, no matter how your opponent plays. Minimum is 3. It can be more, may or may not be the optimal. Right? So far so good. So this is the algorithm. So in quick recap, the algorithm is calculate the minimax value for each node. In order to calculate the minimax value, go bottom up in the search tree. The bottom layer, the leaf node values of minimax value of the leaf nodes are equal to the utility function which is given. From that, try to traverse up the tree and calculate the minimax values. How do we calculate it? For min node, you look at the children's nodes minimax value and you select the min out of them. For max node, you look at the minimax value of its children and you select the value which is the maximum out of all the children's minimax value. And that way you can build the minimax value for all nodes of the tree. Once you have the minimax value of all the nodes of the tree, you get a winning strategy automatically from that. Right? For example, here, because 3 is the minimax value at the max node, your strategy is going to be select A1 and not A2 and A3, because A1 is the node which leads you to a min node whose minimax value is 3. It's a simple game which has just one move as a strategy. We'll see now an example, slightly two move game now, and we will do a dry run of the minimax algorithm on this tree. Right. So this is a game tree. You are given the utility function value of the leaf nodes in this example. Now let's try to calculate the minimax value bottom up, as minimax does. Right. So look at this node. Look at the last but one layer node, leftmost one, min node. It's a min node, so it has two children with value 80 and 30. Right. So out of 80 and 30, the 30 is minimum. So 30 should be the minimax value of the leftmost child. So here, this is the intermediate state. First, the algorithm looks at its left child. It sees 80, it copies it. Then in the next step, it looks at its other child, which is 30, finds that 30 is less than 80, and so 80 is copied. So at the end, the minimax value of the node, the inverted triangle, is 30 because 30 is less than 80. So similarly, you get the minimax value of the node, just the node on the right of 30 as 25, because 25 out of 25 and 35, 25 is smaller. Right. So 25 is the minimax value of this node. Now, because we have the minimax value of both 30 and 25 ready with us, we can calculate the minimax value of their parent, which is a max node. Right. So the max node has two children, 30 and 25, due to two actions. Now, out of these two children due to two actions, 30 is better. 30 is greater than 25. So for the max player, it is always better to move left and go to the node 30 and not 25. Right. So that's why 30 is the minimax value of the max node. If you so if I do similar computation on the right subtree, then see 50, 25, I copy 20 above. Out of 5 and 65, I copy 5 and 5 above in the min node, 5 being less than 65. Now in for the max node minimax calculation, I look at its children 20, which has 20 and 5 respectively as the minimax value. And I would like to choose 20 as the minimax value there. Because the agent can potentially go left action and go to 20 node opponent to a node to a min node which is marked 20. Right. So now 30 and 20, the minimax value of the childs of the min node are ready. Oops, where am I? Right. So out of 30 and 20, it's a min node. So you are going to select 20 eventually. 30, 20. Yeah, you see 20 is finally selected from its children, being a min node. So like that, you also calculate the right subtrees nodes minimax values. Right. So 20 and 15 are the layer 1 node min nodes minimax values. So at the root, the minimax value of the root becomes the max of 20 and 15, which is 20. Now this is your full minimax tree computation after completion of the algorithm. Now once you have this tree, you get a winning strategy also. How? So from from the root, you take out of, say, you have two actions as choices. So you choose the left action, which takes you to a min node, which is 20. So that's your strategy. Right. Now I assume that the min player plays optimally, meaning the min player takes the right move. Right? I think shown in the left, in the last slide here. Right? This is the optimal play. Optimal play. So your strategy, winning strategy at the root is apply the left action. Why? Because that is the action that takes to the min node, which has the value 20. Okay, now at min node, you have no control on how is the player going to play. So let us assume that the player plays optimally. If the player plays opponent plays optimally. If the opponent player plays optimally, it is definitely going to choose the right action, because right action minimizes the utility function. If it would have otherwise chosen the left action, then the utility value that could potentially be obtained is 30, which is more than 20. And you are opponent, you don't want to get a larger or utility function. So you will choose a value which is equal to 20 and you go right. Okay, now you at this second layer, which is a max layer, you again have two options. Out of the two options, left action is leading you to a larger utility function, which is equal to 20, the minimax value. So you would better take the left action. And now at the min node marked at 20, you have two choices, 55 and 25. You are an opponent and your goal is trying to minimize the utility of the game. So your opponent will take the right action and will end in a terminal state which has a utility 20. Right. So this red path shows a play of the game, two move play of the game, where the game ends in a utility function which is exactly equal to 20. And what is guaranteed is, if you follow the winning strategy, if you follow the if the AI agent follows the game with the strategy, which is always choose the action which is going to the node with maximum utility out of its children, then no matter how the opponent plays, you are definitely guaranteed to end in a state whose utility is 20 or more. You can verify. For example, let's say AI agent goes to 20. Now your opponent, instead of going right, it goes to left. Right, so it comes to the node 30. Now your AI, the AI agent has two options. No matter which option it takes, it will always get a gain which is minimum. Yeah, so AI agent will is going to play as per the strategy, which is go left. So once it has come left, no matter how your your opponent plays, you will either get 30 or 80 as an outcome, which is both of them are larger than 20. Right. So this way you can verify that the algorithm ensures that if you follow the winning strategy, then you are guaranteed to get a utility which is 20 or more. Okay, these are some questions. Why do we take the min value every other level of the tree? And the answer is because the min node simulate the opponent, and the goal of the opponent is to minimize the utility function. The computer assumes that the human will choose that move that is of least value to the computer. Here the human is the computer is the AI agent and human is the opponent, and the AI agent always assumes that the human plays optimally. Even if it plays optimally, you have a guarantee of a minimum value that you will always get in the game. Okay, this is an algorithmic description of what we just saw in the pictures above, of how to calculate the minimax value of each node. So the idea is actually just do a depth first traversal of the game tree and get the value bottom up. Carry the value from leaf nodes upwards by doing this min and max calculations. So let's try to quickly browse through this function. Right, so the first function is the decision-making function. This is the function that the AI agent uses to make a decision of which action it should it should choose out of all the actions it has in hand. It's called minimax decision. It takes a state and returns the action as per the strategy. And the selection is made as follows. So it calls the max value function, which is another function we are going to discuss now. It calls max value of the state. And for that max value, yeah, so this V is that successor of the current state, which is having the maximum minimax value. Once you have that V, you return that action which leads the game from the given state as a parameter to this new node V. Okay, that is the best strategy that is selected by the minimax algorithm, right? For example, right? If for example, if you want to make a choice at the root, then look at its children, 20 and 15. Choose the node which is having the maximum value, this node 20. Now, once you know this, find the action which leads to this min node 20 from the given root, which is let's say A1, the red color edge here. Right, now the just a minute. Okay, now let's see what is the max value function doing. So max value function takes a state and returns a utility value. Yeah, so if the current state which is passed to max value is a terminal state, then you only return the utility of that state. So if it's a terminal state, we know that its minimax value is its utility, so we return it. If it is not so, then what we do is we look at all successors of the state in the for loop, and for each of the successor, we calculate the mean value of the successor. We calculate the mean value of the successor and we compare with the running max, which is initialized with infinity. So essentially, once you complete the for loop, the value of V is the maximum of the minimum values, maximum out of the mean values of the successor of the state. Right? The picture will clarify. Max value of a state. Right, so max value of the state 20 is the max value of this state is, look at the successors, get there. Just a minute, I forgot. Max is in successors of state, do max of V comma min value of S. Oh, right. Yeah. So okay. Note that this algorithm, when you run this algorithm, what I want to say is this algorithm is also responsible of calculating the minimax values. It's not that the algorithm, you run this algorithm once the minimax values are computed already somehow. This algorithm is also calculating the minimax values. The way it does is by recursion, right? So if you're trying to get a max value of a state which is a terminal, then you return the utility which is node. If it is not the case, if you're trying to get a max value of a state which is not the terminal, let's say we are here. Let's go to this picture. right? So let's say at the root, I want to calculate the max value of the root. So how do I calculate the max value, minimax value of the root? The way I calculate the minimax value of the root is I recursively calculate the minimax value of the min nodes. And once I have the value of the min nodes of its children, once I have the minimax value of its children's calculated, then I choose which is the maximum and I copy it. But the question is now, I don't even know what is the minimax value of the children. So what to do? So I recursively go down. So for the left child, which is a min node, I call min value function in order to calculate its minimax. What does the min value function does? It looks at the children of the min node, and out of the two children, it calculates the max value of the two nodes because they are max nodes. And once they are calculated, it chooses the minimum out of them and copies it. But again, in this picture, I don't even know the max values of its children. So I apply the same idea recursively and until I reach a node, which is just a node, which is the utility function. And now when the recursion will unroll upwards, it is going to pass on the appropriate values from the bottommost layer upwards, right? So this algorithm is essentially doing a depth first search, right? So like if you follow this picture, you start from the node and look at the black tree, the algorithm will recursively come down until the leaf nodes where the values are known. And this is the point when the recursion will unroll back, and out of 80 and 30, which are max nodes values, you get the maximum, you get the minimum out of them, and you get the minimax value of the last but one node, leftmost min node 30. Right? So this entire backtracking with value propagation upwards is depicted in this algorithm. Right, look at the successors. Call the mean value function. Out of all the mean value function, take that value which is maximum and return it. Now, how do you calculate the minimax value of a min node? In mean value function, you first see whether that min node is a terminal. If so, pass the utility. Otherwise, look at the successors of the min node, and because it's a min node, out of all the successors, choose that node which has the minimum value. Return that value. Okay, finally, last slide, properties of minimax. Is it complete? Meaning that, is it going to terminate and give you a winning strategy always? The answer is yes, if your search tree is finite. If the search tree is finite, then it's going to, of course, terminate. It's depth first search with a bounded tree. It's going to terminate. Is it optimal? Is it going to does it guarantee an optimal strategy? It's not going to give you an optimal strategy. So look at the second point, as we just discussed in the example with 14 node. It's not going to give you an optimal strategy if the opponent is playing suboptimally. However, if the opponent is playing optimally, then the winning strategy that you get is the optimal utility function that you could achieve, is the optimal that you can achieve in the presence of an optimal opponent, right? So if the answer is yes, if the opponent is optimal, and it's no if the opponent is not optimal. What is the time complexity? So you have to calculate the minimax value for all the nodes of the game tree. If your game has a average branching factor of 2, and if your utility layer is m depth away, the leaf, the depth of the tree is m, then you have order b to the power m nodes. You have to traverse all of them. That makes it both space, time-wise order b to the power m. And if you're doing a depth first, if in the algorithm that we saw, we are actually doing a depth first traversal and propagating the value from bottom to up. And depth first search, we know it's the complexity is order BM. Okay, with that, we stop today. Any questions? Maybe I went too fast in the end. Did it make sense?
Yes, sir, it makes sense.
All fine. Okay. Okay, then let's stop here. We meet on Tuesday.
Okay, sir.
Thank you, sir.
Thank you, sir.